In this video, we are going to sketch the graph of this function here. F of x is equal to x plus 3x to the 2/3. We're given the first and second derivatives, though in this case it would actually be quite easy for you to check that these are indeed the first and second derivatives. You may wish to try to sketch this on your own first and then watch the video. Regardless, though, you should include the solution to this problem with your notes. Okay, so as usual, what we're going to do is we're going to sketch a set of axes at the top of the page. So here we have our set of axes, and now we're going to examine our function according to all the different qualities that we've been talking about in class. And first we like to talk about A, the domain of f. So remember, I'll just write this over here. F of x is the function x plus 3x to the 2/3. And what we see is that if you took any number x at all, you certainly could square that number and then take the cubed root of what you obtain. And so x plus 3x to the 2/3 makes sense for any x. And so the domain of this function is actually going to be all real numbers. Okay, so this is just R. All right, next thing that we like to think about is symmetry. This is where we ask, does f of minus x equal either plus or minus f of x? So what we do is we just start evaluating f at minus x and see if we can find either plus or minus f of x in this. So we're just going to replace all occurrences of x in the formula for f by minus x, and we'll have minus x plus 3 times minus x to the 2/3, and that 2/3 I could, notice, write as minus x squared to the power 1/3. If we do that, we notice that this looks like minus x plus 3. Minus x squared is just x squared. So this is just x squared taken to the power 1/3, which we can now write as x to the 2/3. And notice that that doesn't equal either plus or minus x plus 3x to the 2/3, because, well, if we had a plus here, we would just have, of course, x plus 3x to the 2/3. That's not what we have. And if we had a minus here, we'd have minus x minus 3x to the 2/3. We have minus x, but not minus 3. Plus 3 is what we have. In other words, this is not equal to this, which is to say it's not equal to plus or minus f of x. So because f of minus x is not equal to plus or minus f of x, f is neither odd nor even. We'll just say no symmetry in this case. All right, C. Next thing we like to think about are intercepts. So first of all, our y-intercepts. So y-intercepts happen when we cross the y-axis. That's when x is equal to 0, so we're evaluating f at 0. And f of 0, in this case, remember, let's write it again, f of x is x plus 3x to the 2/3. So f of 0 is equal to, well, 0 plus 3 times 0 to the 2/3 is just 0. Okay, so our y-intercept happens at the origin. Put that on in a moment. And what about our x-intercepts? Well, our x-intercepts happen when we're crossing the x-axis, that's when y is equal to 0. So we ask, when does y equals f of x equal 0? Okay, so if f of x, which we know is 3 times x to the 2/3, is equal to 0, well, notice that we can actually factor x to the 2/3 out of the left side of this equation. So this looks like x to the 2/3 times x to the 1/3 plus 3. So we're wondering then, when does this product equal 0? That can happen if x to the 2/3 is 0, which is to say if the factor x to the 2/3 is 0, or if the other factor, x to the 1/3 plus 3 is 0. In other words, when x is equal to 0, or x to the 1/3 is minus 3, and x to the 1/3 is equal to minus 3 when x is equal to minus 3 all cubed. So I cube both sides. That gets rid of the x to the 1/3 on the left. I'm left with x. And on the other side, I have minus 3 cubed, which is minus 27. Okay, so our x-intercepts are x equal to minus 27 and x equals 0. And as we saw before, the y-intercept is also 0. So we have intercepts at the origin and at x equal to minus 27. So we'll put those on right now to our graph. So at 0, the origin, we're going to cross the x and the y-axis, and at minus 27, let's put that right here, say we're also going to have an x-intercept. Okay, so next thing that we like to think about are asymptotes. So D. So first we'll think about horizontal asymptotes. This is where we're really asking, what does our function look like as x approaches plus and minus infinity? And so, starting first, the limit as x tends to infinity of f of x, that's equal to the limit as x tends to infinity of x plus 3, x to the 2/3. In fact, this is the sort of function to which our theorem for evaluating limits at infinity applies. So I could actually drop that lower power of x, 3x to the 2/3, but we can also just do this manually by factoring the highest power of x that we see here, which is to say x. And we see that we are left with 1 plus 3 over x to the 1/3. And, well, what happens here is this 3 over x to the 1/3 is going to tend to 0. So this entire factor here is tending to 1 plus 0, which is 1. X is getting big, and the overall limit then is going to be, well, as big as you like. The limit then is equal to infinity. All right, so equal to infinity. And similarly, we can take the limit as x tends to minus infinity. F of x, I'm just going to factor that x out right away. Limit as x tends to minus infinity. We'll have x times 1 plus 3 over x to the 1/3. That second factor, again, is tending to 1 plus 0. And the x part is tending to minus infinity. So large negative times something close to 1 is going to be a very large negative. The overall limit is minus infinity. Okay, so we don't have any horizontal asymptotes, but this does tell us something about our function. It says that as x becomes large and positive, f of x becomes large and positive, and as x becomes large and negative, f of x becomes large and negative. So let's let's just indicate this on our graph so that we won't forget. As x becomes large and positive, f of x is going to become large and positive, and as x becomes large and negative, f of x is going to become large and negative. All right, so on to vertical asymptotes. Remember, vertical asymptotes are going to occur, if at all, at points not in the domain of the function. In this case, well, the domain of our function is equal to all real numbers, and so we're not going to have any vertical asymptotes. So let's just write that down. So there you have it. Because the domain of our function is equal to all real numbers, we're not going to have any vertical asymptotes. When looking for vertical asymptotes, we would look at points which are not in the domain of the function. All right, so moving on. Next thing we look for are intervals of increase and decrease. Where is our function increasing and decreasing? For that, we look at the sign diagram of f prime prime, rather of f prime of x. All right, so we're looking at the sign diagram of f prime of x to see where f is increasing and decreasing. So first we need to find the sign diagram of f prime of x. F prime of x, remember we were given, is equal to x to the 1/3 plus 2 all over x to the 1/3. And that is going to be equal to 0. So when we're trying to find a sign diagram, we look for places where our function takes the value 0 and where it's discontinuous, which is to say where our functions don't exist. Okay, so this function is 0 when the numerator is 0, which is to say when x to the 1/3 plus 2 is 0, which means x to the 1/3 is equal to minus 2, and cubing both sides, we get x on the left is equal to minus 2 cubed, which is minus 8. Okay, so f prime of x is 0 when x is equal to minus 8. And where does it not exist? Well, when the denominator is 0, which is to say when x is equal to 0. So if we write that down, f prime of x does not exist when the denominator, x to the 1/3, is 0. That is when x is equal to 0. And notice that these are both critical numbers of f. Critical numbers are those values in the domain of the function where either the derivative is 0 or the derivative does not exist. In this case, both minus 8 and 0 are in the domain of the function, and these are the places where the derivative is 0 and does not exist. So these are both critical numbers. Let's just note that. So this is a critical number, and x equal to 0 is also a critical number. Okay, so now we want to find our sign diagram for f prime. So we place those points where the derivative is 0, in this case minus 8, on our number line with a solid dot, and where it does not exist, in this case 0 with a hollow dot. And we notice that in this case both minus 8 and 0 are critical numbers. we can find the sign diagram now for f prime just by noting that, as usual, our function f prime in this case cannot change sign on any of the intervals determined by these two numbers. So to find the sign diagram, the sign of f prime, for example, on minus infinity to minus 8, you just have to evaluate f prime at some value in this interval. And similarly here, if you check, you would get, I'll let you check this yourself, that it is that f prime is positive on this interval, negative on this interval, positive on this interval. And what that tells us is that f is increasing from minus infinity to minus 8, decreasing from minus 8 to 0, and increasing from 0 to infinity. Because by the increasing-decreasing test, we know that a function is increasing when its derivative is positive and decreasing when its derivative is negative. Okay, so now we can move on to find our local maxes and local mins. So what is that? I guess that's f. And what we know from Fermat's theorem is that the only place where a function can have a local max or local min is at a critical number. So we just need to look at these values here, minus 8 and 0. These are places where f had a critical number. All right, well, from the first derivative test, we can see that because we increase towards minus 8 and then decrease beyond minus 8, we're going to have a local max at minus 8. And because we decrease towards 0 and then increase beyond 0, we're going to have a local min at 0. So let's just write that down. All right, so now we need to know what the corresponding y values are when x equals minus 8 and x equal to 0. In other words, what is this local max at minus 8 and what is this local min at x equals 0? So first of all, evaluating f at minus 8. Notice f of x, remember, is x plus 3x to the 2/3. So this is going to equal minus 8 plus 3 times minus 8 to the 2/3, which I'm now going to write as minus 8 to the 1/3, all squared. And we'll do it like that, because note that minus 8 to the 1/3, well, it's that number with cubed equal to minus 8. And minus 2 cubed is equal to minus 8. So minus 8 to the 1/3 is minus 2. So we have minus 2 all squared here, which is equal then to minus 8 plus 3 times 4 is 12, which is equal to 4. So that's our local max at x equal to 8. And at 0, what do we have? Well, f at 0 is equal to, again, looking at our function at 0 plus 3 times 0 to the 2/3, that's 0 plus 0, which is equal to 0. We actually already evaluated f of 0 when we were looking for our y-intercept. So f of 0 is equal to 0. Okay, so we now know that at minus 8, our y value is 4, and that's going to be a local max. And at 0, our y value is 0, and that is going to be a local min. So let's put these points on the graph now. So we're putting the point minus 8, 4 on the graph. So let's see, minus 8's around here. And 4 is here. And remember, f prime at minus 8 was actually equal to 0. So we're going to have a horizontal tangent line there. So I'm just going to indicate that by drawing this horizontal line here, small horizontal line. And what was the other point we wanted to put on? That was the point 0, 0. We actually already put the point 0, 0 on. That's the origin. And remember, f prime of 0 did not exist. So this was one of those critical numbers where the derivative didn't actually exist. So in this case, we don't want to indicate that we have a horizontal tangent line at this critical number, well, because we don't have any such thing. All right, so last thing we want to look at is concavity of our function, and in the process we'll find all of our inflection points. To find what the concavity of our function looks like, we form a sign diagram for f prime prime of x, the second derivative of f. So, if you recall, written down at the top, f prime prime of x, we were told, is equal to minus 2 over 3 times x to the 4/3. And, well, when is that going to equal 0? So that's going to equal 0 when? Well, the only time that it could equal 0 is if the numerator is 0. So that could happen if and only if minus 2 is 0, which of course is never. All right, so f prime prime of x is never equal to 0. And f prime prime of x does not exist exactly when the denominator is 0. That's going to happen when x is equal to 0. Right, so let's form our sign diagram for f prime prime. We put all places where the derivative is, where f prime prime is 0. Well, that's never on the sign diagram. And all places where f prime prime does not exist, that is 0 on the sign diagram. And, well, in this case, actually, it's quite easy to see that f prime prime is always going to be negative. Maybe I'll just notice that f prime prime of x can be written as minus 2 over 3, and that x to the 4/3 could be written as x to the 1/3 all to the 4th. And looking at this, we see that this numerator, minus 2, that's always negative. And the denominator, because we have this 4th power here, is always going to be positive, so it's always negative over positive, which is going to be negative whenever it exists. So it's always going to be negative. So f prime prime is negative to the left of 0, negative to the right of 0. And we know that f is going to be concave up whenever its second derivative is positive, concave down whenever its second derivative is negative. In this case, f prime prime is negative from minus infinity to 0, so f is going to be concave down on that interval, and f prime prime is going to be negative from 0 to infinity, so f is going to be concave down on this interval here. All right, so in fact, we probably should have written before precisely those intervals on which f is increasing. And we should write here where f is concave down, so let me just write that. All right, so I've explicitly written f is concave down on minus infinity to 0, and also concave down from 0 to infinity, and also, because I had forgotten to do this, let's just slide up here. I also added here in yellow explicitly f is increasing, as we saw, from minus infinity to minus 8, and also from 0 to infinity, so written there. We saw that it was decreasing from minus 8 to 0, so I've written that there. Again, looking here where we described the concavity of f, we saw that f was concave down everywhere. Remember that an inflection point is going to be a point on the graph of your function where f changes from concave up to concave down, or from concave down to concave up. In this case, the concavity of f is not changing at all. We definitely have no inflection points. So let's just write that down. No inflection points. Okay, so everything that we needed to say, we've now said. Now let's finish the sketch of our function. Finally, we just need to put all of our information on our graph. Well, we already put a lot of information on our graph right here. Here are my x-intercepts at -27 at 0. We knew we were going to have a local max at -8 and a horizontal tangent, a local min at 0 and no horizontal tangent. And as x tended to infinity, f was going to tend to infinity. And as x tends to -infinity, f of x is going to tend to -infinity. So the only thing that we need to look at now are at these two sign diagrams for f prime and f prime prime, and put this last bit of information onto our graph. All right, so we see that from -infinity to -8, our function is going to be increasing everywhere, and it's going to be concave up. All right, so we are going to draw it so that our function tends to -infinity as x tends to -infinity, and it's going to be increasing all the way until we get to -8. We're going to cross the x-axis at -27. We're going to have a horizontal tangent line at -8, and it's always going to be concave down on this interval. So let's draw that now. First, I'm going to just get rid of this bit right here. And let's see what we can do. And so increasing, concave down. And there we have that horizontal tangent line. Now, what are we going to have? Well, from -8 to 0, it's going to be decreasing, and it's still going to be concave down. So let's draw that with no horizontal tangent line at 0, where we're going to have a local min. Okay, so decreasing and concave down. And now what happens? Well, from 0 to infinity, our function is going to be increasing, concave down, and we're going to tend to infinity as x tends to infinity. So first I'm just going to erase this thing here. And we'll draw it accordingly. So I'm going to draw it so that it's concave down and increasing, and is tending to infinity, something like that. And that's it. So this looks like the graph of whatever our function was. It was y is equal to x plus 3 x to the 2/3. So there it is. And notice that in this case, we had this cusp here at the origin, and that's not really surprising because remember, at 0, we had the sort of critical number where we were, of course, at a point in the domain of our function, but where the derivative did not exist. So no surprise that we have this cusp here, and that was because we decreased towards here and were concave down, then increased beyond here, but remained concave down. That created this cusp. All right. So that's what this function looks like. Wow.